Well, howdy again, folks. Mr. Bleecker here with a lesson on acids and bases. What are they? We'll define it. And you might have heard of something called the pH scale. We'll focus in on that. So away we go. So acids and bases will burn you in different ways. Now, if you're looking at this symbol here, WHMIS, this is also, you'll see this in the global harmonized system, where they talk about items that are corrosive. Acids and bases are, you have to describe their burning action, and I want to describe it as a burning action in different ways. Acids will corrode metal, but that's not what bases do. Bases are caustic, right? And if you get a base on your skin, it will burn you just like an acid would feel like it was burning. But they're having different chemical effects. If you think of that burning sensation, well, acids and bases kind of go about that differently, but we'll talk about that in this lecture. Newsflash, if you get it on your skin, wash with lots of soap and water and get it off right away. If you get something like that in your eye, you have to flush out your eye, get to an eye wash station, and then always seek medical attention for an eye injury, needless to say. So when we talk about acids, acids are what we refer to as sour, which is why we love sour candies. Sour candies will often have acidic compositions, and I've had some sour candies. I remember some roommates of mine at university brought me these. They looked like sort of like gobstoppers, those hard candies, and they were covered in this powdered acid. And it was a neat story. They brought it to me, and one of them was my secret sister, and she wanted to. There were 3 people standing at my door, and they said, "Try this." And it was the most sour thing I have ever tried. And I think my face turned completely upside down, much to their my dismay. Acids are sour, so we'll talk about things like lemons, limes, right? Things like that, right? A lot of citrus fruits, you can see them on the sour side, right? Hot sauces, if you like really spicy things, a lot of those things are coming from vegetable material or even fruits that can be quite sour, right? Bases are different. Bases are bitter. And if you don't believe me, I always say, don't do this, but a bar of soap, right? When my brother was younger and his language got away from him a little bit, and he had to have his mouth washed out with soap. Yes, that's actually happened to some people. Bases, like soap, and soap is a base, are extremely bitter. Extremely bitter. And we think the reason why we're so attuned to these bitter flavors is that a lot of things that are poisonous tend to be on the base side, and our taste buds are very attuned to the bitter, okay? We know. So acids and bases, as we talked about this, different kinds of burning, right? Corrosive. Now by corrosive, what's happening to metal is it's literally dissolving. So if you dissolve metal with an acid, you'll get hydrogen gas being produced, and that's flammable. That's nasty, right? Bases, on the other hand, we don't say they're corrosive, we say they're caustic. And sure, it feels like they're burning, but this doesn't corrode metal, okay? Does not. And the reason why bases are useful to us are when you go to clean your stove, you want to put a base on all that burnt on yucky material, and that will be removed, right, through a caustic process. But if you used an acid, that would be horrible because you would actually be breaking down the metal lining of your stove. Bases don't do that. So the most common base we use with, for example, Easy Off to clean an oven is something we call sodium hydroxide. And it's pretty concentrated, right? You really don't want to get that on your skin or in your eye. But it's caustic and it removes the buildup, and hey, you got a nice clean stove again, okay? And I've written over top of it, but it says the strength of acids and bases is measured on the pH scale. So what's the pH scale? A way of understanding what pH means is just sort of a way of understanding it is you can say the proportion of hydrogen. Now, in this case, we're talking about hydrogen ions, okay? You're going to study a lot of chemistry around hydrogen ions, hydroxide ions a little bit later. So we're looking at the concentration of these things. And that's what bases do. They release hydrogen ions into solution. So if we have a solution where the amount of acid and base are equal, like this is why I love to write water this way. You know water is H2O, but I like to write it in both its forms. Remember how I said hydrogen is the first element in the periodic table, and in old periodic tables they have it as a metal and a non-metal, because when you're number one in the periodic table, the first element in existence, you're going to have characteristics that lead to all the elements in existence, right? So hydrogen can act in a metallic way. This is hydrogen hydroxide. This is the ionic formula here. That's when we consider it functioning as a metal, but you can think of it as covalent if it were sharing electrons, and we often describe water that way. It's both. I want you to look at pH 7 here, and I want you to understand why it is neutral. Now, acids release these into solution, okay? And bases release something else into solution, okay? We're talking about hydroxide ions. They form them, okay? When you look at water, it's HOH, right? 1 part hydrogen, 1 part hydroxide. That's balanced. So when we look at pure water, nothing else in it, like for example distilled water, that should have a pH of 7. It's balanced. Hydrogen ions, hydroxide ions, balanced. But as you go to the left, this direction, you're getting more hydrogen ions in solution. And the more and more concentrated those hydrogen ions, the more it's going to, the more it would burn, right? Something down around pH 0. Check out, your stomach is checking in at around pH 1 when it's in full use, right? It's like, for example, if you're digesting a steak, your stomach will produce hydrochloric acid like crazy. That's really strong, right? Here's a tomato, citrus fruits. You can see that these are actually quite acidic things. And with underripe grapes, you'll taste that. You can taste that. If there isn't as much sugar produced yet, the sour will come through. Now, looking at milk, I always thought it ironic, right? Milk, you have an acidic stomach, you figure, oh, milk will be great. It'll help to, all milk's doing is it's a weak base, pH 6. It's kind of watering down that stomach acid, right? It's helping to ease it. But milk itself is kind of acidic. As you become more acidic, your pH goes down, and we'll talk about what that means in a minute. As you become more basic, your pH goes up in this direction. So this would be more of the hydroxide ions. And the more hydroxide ions you get, the stronger the base you are. For example, there's bleach. Now, there's very little, as you get over to this side over here, you're not going to see as many hydrogen ions, right? They become less and less plentiful, lower concentration. And as they become lower in concentration, that number goes up. So here's a way to remember this. As you get down to 0, heading towards pH 0, it's becoming concentrated for hydrogen ions. As you go from pH 7 to the right, like oven cleaner is coming up on pH 13, you're increasing the hydrogen or the hydroxide ion concentration, and you're becoming less acidic. You're becoming more basic. All right. So, 14-point scale. So pH, when we talk about pH, later on you'll study something called pOH, which is the proportion of hydroxide. But here, when we're talking about pH, we're talking about the proportion of hydrogen. So we're looking at it sort of in that sense. It's a bit like the earthquake scale. It's logarithmic, and I know that's a big word, but those are just powers of 10, right? And you guys have studied the decimal system. You know powers of 10. So Powers of 10. So what we're going to look at it is how much hydrogen is in solution as a power of 10, or as a power of tenths. It could actually get less. Powers of 10. Okay. So as you go down, as you go from 7 down towards 6, down towards 5, etc., the concentration of hydrogen ions becomes 10 times stronger. Every time you go down a whole number, right, the amount of hydrogen is going up. And I kind of like writing the 10 over top of the arrows, because you get a sense. I'll have to stop there at 2. You can see, if we think about starting at our pH 7, and if we jump from pH 7 to pH 5, you've gone through 10 times 10 times. So 5 is 100 times more concentrated for hydrogen ions than 7? Yep, because each one of those is a factor of 10. So pH 4, 10 times more acidic than 5. All right, I'm starting to get this. pH 3, well, 3 is 1, 2, 3 categories away from 6. And remember, every time you go down, right, to a whole number, that's a power of 10. So 10, 100, 1,000. So grapes are a lot more acidic than milk. In fact, they're on average 1,000 times more acidic. Okay, so when it comes to determining how do we determine pH, how do we know if something's an acid or a base, there must be some way to test it. And you guys are thinking, well, there's probably a probe you can put in there and you can figure out what's going on. And that's very true. There's a variety of methods. The easiest method is to put in a chemical that will change color. Now, when it changes color, there's a whole forest of chemicals out there, folks, that we can use. We'll just look at a couple, some simple ones. These are called chemical indicators, and sometimes they'll tell you whether or not you've got an acid or a base, and some of the indicators can go through different sort of color ranges. We have a really great lab that we do at College Heights with chemical indicators, and I hope we can get that one done this year, or make sure we do it next year, because it's bang on what you need to know about acids and bases. But we'll talk about something called litmus paper. Now, litmus is an interesting, it's an interesting material. Litmus all right. Litmus paper. Litmus paper is this interesting paper that will change colors depending on what environment it's in, right? There's red litmus and there's blue litmus, and it's kind of neat. Here's the blue litmus paper here, right? Here's an example of litmus paper being used in different solutions. But litmus it's a chemical that comes from a lichen. Now, you don't know about lichens, right? But lichens are those fuzzy things that grow on trees. These things. This is known as a foliose lichen because it's like foliage. And it produces certain chemicals, and when we extracted them, they're actually very sensitive to acids or bases. So there's a blue chemical that we extracted, and there's a red chemical. So we came up with this blue and red litmus paper. It's pretty cool. Now, the red litmus will be used to tell us about a base, and the blue litmus will tell us about an acid. And I know that's kind of interesting, but let's show you it in action, okay? So here we go. This red litmus paper here started out red, and what they did is they have basically a beaker, right? They'll have a beaker of stuff. So I'll just draw my worst beaker ever. Even with an Apple pencil, this is fun. And if we dip this in here, right, and it's red normally, and it changes color to blue, that'll tell us that this is a base. Red litmus changes to blue in a base. Okay? Below, we have a different scenario. We have blue litmus paper. So this is the part that hasn't been dipped into anything. So, oops, go back. This was a base, right? And we know that that has hydroxide ions in it. That's the only reason it'll turn blue, because that is a chemical reaction that makes the red paper turn blue. Okay. Conversely, draw another beaker down here, quick one. Right. Oh, Mr. Bleeker's beakers are terrible today. All right. If we dip the blue litmus paper in there, I'll just have to say B, like this. And if this changes to red, so if that turns red, something must have made it change. This blue litmus paper, when it turns red, it's because there's an acid. There's a chemical reaction with the paper, and that's basically it. So when red litmus paper goes blue, that's a base. If blue turns red, that's an acid. Right? More to memorize. I know, it's great fun. Like I said, we've got lots of different kind of chemical indicators, and they can change color, not just when you looked at litmus paper, all it can tell us is whether or not something is an acid or a base. It doesn't say a power of 10. It just says well, if you put red and it changes blue, well, right? That must have been a base. And if I take blue litmus and I stick it in the liquid and it turns red, well, that's an acid. But there's a whole range of indicators. Bromthiamyl blue, which is kind of cool. It only changes color in a very specific range, like this, right? It's blue, but when the pH gets around that range, right, it'll turn yellow, which is pretty cool. Anything outside that range, right, it tends to stay blue in a base. So this is where you'll get a color change. Phenolphthalein, which turns out to be one of the lead components in X-Lax, one of those laxatives, it's really good for telling us this range, right? And phenolphthalein, it's colorless, but when you get to about pH 8.2, all of a sudden the colorless goes pink. When you do chemistry 11, you'll do titrations, and you'll try to find a really tight equivalence point, right? When you're pretty much coming up on balancing or neutralizing an acid with a base, and you gotta pay attention to that when that pink starts to show up. It's really hard to see. Beets and cabbage. Some of those, if you get purple cabbage, you can actually use that as an indicator too. But it'd be better to see in class. Another thing you can do to determine pH, you can use different solutions that turn different colors, right? I get the litmus paper, and I get the bromthiamyl blues, right? There's lots of them. But when you have these things in concentration, you might know that the battery in your vehicle is really acidic. Battery acid is nasty. Now you have to ask yourself a question. Why is it that they have acid in a lead acid battery? Because that's what you get. That's what you put in your boat. That's what you put in your vehicles. Okay? It's a starter battery, even in electric vehicles. So assisted one, for example, I drive a Prius, and I've got a starter battery, right? It's not all electric. So you have to have a pretty strong chemical solution. You think about a battery, it's got a positive end and negative end, and there's a flow of electrons. But for a flow of electrons, you want to have a friendly environment, a liquid environment called an electrolyte. Inside of your battery, right, if you think about your car battery, and this is just a quickie drawing, so I'll just say, positive and negative, there has to be an electrolyte. And that's a liquid solution that has ions in it. Ions are great for conducting electricity, right? You don't want to be in water, especially salt water, right? If there's an electrical discharge, that would be a disaster. Salt water is extremely conductive because of all the ions in solution. Because the flow of electricity, if we think about that, flow of electricity, if it flows more easily through the solution, right, that can actually tell us the pH. The more, well, if you think about the pH of a battery, right, that's around, let's put it up here. A battery has so much hydrogen in solution that its pH is around 1. And we'll talk a little bit more what that means, but that's, if you think about pH 7, that's extremely concentrated for hydrogen ions. If it's extremely concentrated, current's going to flow very easily in that solution. So what we do at pH meter is we just stick a probe and it measures the conductivity of the liquid. The more conductive, right, the lower the pH. I used to work in a lab and I used these things all the time. Sometimes it was a glass probe, sometimes it was a plastic probe. Basically, it just conducted electricity through the solution and measured how easily or how not so easily that it would flow. pH meters. So, in order to know whether or not something is an acid or a base, what you want to do is you can use indicators, right? But now we're going to look at it from chemical standpoint of chemical formula, right? Acids are often written like this. We would say hydrochloric acid, right? If that were dissolved in water, right? And that's liquid hydrochloric acid is always part water. I mean, you don't want solid hydrochloric acid. Doesn't make sense. Unless it were a powder, you could do that. But we say that it's aqueous. That means it's dissolved. You've probably seen these symbols, right? S for solid in a chemical reaction, right? G for gas. And the only one that you would write L for liquid, and I'm just doing a cursive L here, folks, that's always water. Because water is like the universal solvent. We dissolve things into it, right? When we dissolve things into water, we say if something's dissolved into water, we say that it's aqueous, like that, okay? This is just a quick little point about, because acids release hydrogen ions, that's really good for conductivity, right? That's why your battery acid's so strong around pH 1. We do have some acids that are kind of interesting. If they're organic, like for example, coming from a tomato, CH3, COOH. If it's organic, we write the hydrogen on the right because, you know, carbon is so important, right? That's acetic acid, also known as vinegar, right? That's the only time in most acids we write the H last. Most acids, hydrochloric acid, H2SO4, sulfuric acid, right? HNO3, nitric acid. And you notice these, I'm describing these in a certain way, right? But if they didn't come from an organic source, by organic, right, we're talking about carbon and hydrogen in long chains, and this is definitely a hydrocarbon chain here. This one here, and we'll just call it vinegar, right? That's an organic acid, and when it comes to organics, carbon is the boss. So we write it first. It's one of the few times we ever put H at the end. Here, every time you'll notice, in the inorganic acids, it gets top spot. Okay, so here we go. Hydrochloric acid, nitric acid. Now, this one here, acetic acid, okay, we're talking about vinegar, just sort of a common name. And vinegar is sour. If you like pickles, right, it's the sour that gets you going. Why? Well, because it's acidic. H2SO4, and the way that should be written, sorry about that number there. There we go. We're supposed to write these as subscripts, but anyways, it's there. So bases like acids are not about H+. We're not talking about hydrogen ions. Here we're talking about hydroxide ions, right? And if you look in a table of common ions, OH minus has a 1 minus charge, is always called this, hydroxide. So you could call water, if you want to think of it in its ionic context, you could say hydrogen hydroxide. That's not wrong. But we almost always just say, well, here's the name for it as a covalent, dihydrogen monoxide. It depends on how you think about hydrogen. If you think about it as a metal, it can act in a metallic way, right? Ionic. And if you think about it sharing electrons, covalent. That's not really much different. Actually, remember light, it travels in a straight line, right? And it also travels in waves. There's two ways to think about some things. And hydrogen being the first element in existence with helium after the Big Bang, it kind of gets top spot. Okay. So, because hydroxide it's pretty intense, it's also quite caustic, and that'll give you that nice burning sensation on the skin, right? But it doesn't corrode metal. So here's some famous ones. Sodium hydroxide. In outhouses, often you'll see a tub of like white powder left behind, and people will drop sodium hydroxide into the outhouse to sort of neutralize that acidic decomposition that's going on to reduce the smell, right? If you have cat litter, you add a base. For example, you add baking soda. It's in a lot of cat litter. Why? Because it reduces the decomposition. It's not as acidic. You don't get the byproduct gas smell. So it's not a bad thing. Magnesium hydroxide is also known as milk of magnesia. And I always have to stop because kids are like, what are you talking about? Well, if you get a grumbly tummy, right, you have a horrendous acidic gut, and you go to get something to neutralize that stomach acid, milk of magnesia, it comes in a blue bottle, right? It's this stuff. We'll just go with that one. Characteristic blue bottle. And milk of magnesia is, well, pretty helpful because what you're going to do is you're going to neutralize some of your stomach acid, because bases, being the opposite of acids, help to neutralize things, right? If you've got a really, really acidic stomach and you take about basically a tablespoon of this stuff, right? You follow the instructions, usually about a tablespoon has always worked for me. It'll settle your stomach down. Milk of magnesia. Now the formula, there we go, is right over here, MgOH2. And why? Well, I'll write it at the top. Magnesium, as a metal, has a 2+ charge. Hydroxide has a 1- charge. So we're going to need 2 of those. So how do you write that? You write that as magnesium, and you put the brackets around the hydroxide because you need 2 of them. Done. There's other hydroxides. There's calcium hydroxide, ammonium hydroxide. The list goes on and on. These are your cleaners, right? A lot of bases. We're cleaning with bases all the time. Soap, right? Drain cleaner, when you get that big hair plug, like my daughters love to leave in the sink. They don't know they're doing it, but that's what's happening. Toilet bowl cleaner, right? Because bases don't corrode, you don't want to flush acids down your pipes. I mean, it's one thing if you have plastic pipes, PVC, but if it comes into contact with metal or your metal sink, that's not good. That's corrosive. So keep those acids away from those metals. All right. So where do we go from here? Well, if you want to compare them as list items, right? Acids are basically from 6.9 pH all the way down to 0. Now I'm summarizing with 6.9, right? And we could say bases, I'll just choose 7.1, even though it could be 7.0 yada, all the way up to the nightmarish pH of 14. Okay, don't be impressed by the number 14. Don't go chasing it thinking because it's a bigger number that means it's a stronger acid. No. Acids become more concentrated when you're heading towards the number 0. They become less concentrated, way less, when you head towards the number 14. I know, it's a little backwards from your thinking, but, right? 0 is, if it was pH 0, pretty much every ion in solution would be a hydrogen ion, and that would be strong. That would burn the daylights out of you, okay? So, we've kind of looked at the litmus paper thing. They both have aqueous in their formulas, right? Now, here's the thing. This will conduct in solution, and so will this. They're both electrolytes, positively or negatively charged particles, but they have different charges, right? So based on the charge polarity, you can tell whether or not you've got an acid or a base. So they both conduct electricity, just in kind of different ways. Bases start with an H, HCl, unless it's an organic acid. Let's pick one we haven't had. One of those, right? And for hydroxides, well, the go-to is sodium hydroxide, right? We saw calcium hydroxide. I won't try to be too original here, right? Ending in an OH. That's a dead giveaway, right? Just like this is a dead giveaway on this side. Beauty. So when we look at pH for every unit, so remember it starts out as 7, and we'll just write a couple of these on this side, right? 6, 5, 4. Heck, let's throw in 3. When we say that a pH is rising, because we're going in this direction, right? Every jump is a power of 10. Every single one. I missed one. Haha. Throw it in. And last one. When you see all those powers at 10, you can see really you're getting pretty concentrated as you go to the left. But what about when you go to the right? If you go to the right, you're not increasing by 10. If I draw this way, you realize that going the opposite way is a tenth less. So I just wanted to show you that. As you head from strong acids, right, to weaker acids, you can see why. The amount of hydrogen, right, the proportion of hydrogen starts to go down a tenth each time you jump. And that's the reason we call this logarithmic. It's powers of 10 increasing to the left, but it's powers of tenths decreasing to the right. Tell you, math is everywhere. Bam. So now, okay guys, if you know your exponents, 1/10 is the same as 10 to the minus 1. So as you go this way, right, you got 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. You notice that number's going up, tenths, hundredths, thousandths from your original position. Okay, so you're supposed to know your exponents. We'll ease you into it. So if we're going in this direction, you're going up by powers of 10. The pH of 7 is, well, ask yourself. Mr. B had this example. That's got pH 7. Pure water. pH 7. Why? Equal proportions, right? So the pH of 7 is what we call neutral. That doesn't mean it's not acidic. That doesn't mean it's not basic. It just means the acid and the base portions are balanced. So anything less than 7 is acidic, and anything more than 7 is basic. So pH 2, if you think about pH 2, so let's write 2 and 3 like this. If you go from, if you do that jump, right, pH 2, you're heading to the left, is going to be 10 times. Now, you could say 10 to the first if you want, right? But we just say it's 10 times more concentrated. pH 10, okay. So if we had pH, let's put pH 8, pH 9, at pH 10, you can actually count the jumps and you'd be like, okay, so it's getting weaker. So that's like a tenth. And then it jumps another tenth. So now this is 1/100th. Now what is 1/100th as a power of 10, right? Or we could say 10 to the minus 2. Remember with your exponents, See the number of zeros on the bottom of there? Right, there's 2. It's no surprise that that number is 10 to the minus 2. That's just a quick way of doing it, right? pH 1. pH 1, pH 5. Well, now this time, to save time, I'll just count the jumps. 1, 2, 3, 4. Okay, so that's 4 jumps. So we could say it's 10 to the 4 times stronger. If you want to expand 10 to the 4th, right, write a 1 and then put 4 zeros in. That's 10,000 times. pH 1 has 10,000 times more hydrogen ions in solution than pH 5. Holy, look at all the math. Madness. Okay, so moving on to our next one. There's a lot to this section, but hydrogen chloride, we often get our bases in powdered form, right? So it'll be hydrogen chloride, and I know that sounds sort of strange, but when you dissolve that in water, what you get is you'll get hydrochloric acid. So we'll write that in, hydrochloric acid. Yeah, I never leave myself enough room to write, okay? And you'll kind of notice the name, like hydrochloric acid. Well, hydrochloric acid is what we call a binary acid. Now, binary is a word that means 2. There's just hydrogen and there's just chlorine. So there's just that and there's just that. Now, here's a naming convention that you gots to know, so make sure you know it. There's a rule when there's only 2 for all binary acids, you do hydro. Like, you've heard hydrochloric acid. Now you're going to know why we call it that. You say hydro, and then you're like, okay, we know there's hydrogen, so, okay, that's fine, right? What is the second element? You're like, well, it's chlorine. So you take the second name, you don't say chlorine, you kind of just say ick, and then you say acid. Now, I remember my professor saying, hydro, whatever the root name is of the second element, in this case chlorine, acid. He used to call them the hydrorootic acids. By root, he was just saying root name. So you could have hydrobromic acid, you could have hydroiodic acid. You just don't say like hydrochlorinic acid. I mean, that just doesn't sound right. So they kind of shorten the name to the root, so they say hydrochloric acid. And you get to know these really well over time. So you've got hydrochloric acid in aqueous form, right? And it's not quite showing my top line correctly, but you used to have, there's this "ide" portion here. If you have HCl, right, and it's a solid, right, if it's not dissolved in water, it's not aqueous, then you could just call this hydrogen chloride. And that's, we ship it that way, right? Powdered acid. Remember those gobstoppers I talked about that were really, really, really sour, right? Because they had a bit of mild hydrogen chloride dusting them. But as soon as that hit my mouth, right, and it's not very strong, they didn't put a lot on there, it became more of an acid in solution, and then, boy, do your taste buds ever pick up on that. Hydrogen bromide, which is the solid form of that chemical compound, we'll just put in the name, hydrobromic acid. There's the hydro, the root name with that ick, and then acid. So if there's 2 things that make up the acid, you've got to do this hydrorootic acid name. Same thing here. We only see hydrogen playing with one more thing. Now notice that's not a polyatomic. We're talking about 2 elements together forming an acid. That's what we mean by binary acid. So again, you say hydro, and that's iodine. So I say hydroiod, then I throw in the ick, and then acid. Binary acids are easy to name, okay? Some of them more, some of them, when you look at this, okay, we know this is vinegar, and it depends on how strong it is. Ethanoic acid and acetic acid, we're talking about the same compound. That's just different references to how strong they are. The colloquial name is vinegar. But in this case, if we're going to look at this, a simpler name, a naming convention, because it's acetic, right? Also known as acetic acid. Ethanoic acid isn't, just think of it as a synonym for now. There is the acetate ion in there. So CH3COO minus is polyatomic. So wait a minute, hold on. I can't do the hydrorutic acid name. You want to know why? Because it's not two things anymore. We're going to have hydrogen combining with this guy. So now, because it's a polyatomic, we drop that hydro thing. That's gone. So what we do is we just go with the name of this, right? What is that? That's a polyatomic. It's known as acetate. This is going to become the new root name. So we say acetic acid. You notice they're still doing the ic, but the hydro is missing. So if you've got a polyatomic ion combining with hydrogen, you have to call the polyatomic ion by name. That becomes the root. So that right there has to be a part of the acid name, acetic acid. Okay? If we look down here and we say, okay, what the heck is that? Well, okay, so that's sulfate, right? So you had sulfate, and what goes, this is really the root portion right here. So you kind of eliminate, you kill the 8 part, right? That's what happens. So we would call this, because that's the sulfate ion, we call this sulfuric acid. So I call these the ic acids because as soon as a polyatomic combines with hydrogen, you've got to go with the root. So we'll take the root-ic acids, the rootic acids. Okay. This one is sulfite. Okay. So it's a little bit hard now because you're saying, wait, hold on a second here. Hang on. We got SO4 and we've got SO3. Okay, this is an 8 sulfate and this is sulfite. You're like, shoot, what am I going to do here? Right? Because it can't be an ic acid. It's not one of these. So, you know naming conventions. When it's these guys, you do ic. And when it's anything that ends in ite, you say us. Wonderful, isn't it? So now you don't say sulfuric acid, because we're looking at the sulfite ion, you have to say sulfurous. So these are the us acids. And the us acids have a polyatomic that ends in ite. Like chlorite would be another example of that. That would become chlorous acid. People are like, oh my goodness, you're killing me here. Yes, you must love naming. We all suffered through it. At the bottom, what do we got? We look at it, we say, hey, that is nitrate. Okay, it's got the 8, which means it's going to have the ic in its name. So we say this is you drop the 8 and you say ic, and then you have to say acid. Perfect. Over here, carbonate is the ion. Drop the 8 and you say carbonic acid. And you find that in soda. It's also floating around in your blood. You don't have CO2 bubbles floating around in your blood, ladies and gentlemen. Your CO2 gets back to the lungs in liquid form. True story, you heard it here first. Or maybe you didn't. Maybe you picked this up at another grade. Okay, so famous names. Holy moly. You know what you need to do? These are practice questions. So I'm going to do that famous pause. And then you're going to come back and you're going to see if you could answer these. So remember your binaries. right? Example, HCl. Remember your, your 8 acids, your 8s, right, which would be like H2SO4, because these will be your X, and your ites, which would be, well, H2SO3. Let's have fun with that, because that's the sulfite ion. This would be the US. Let's see how you do with these. So, pause. Okay, so now that you're back after banging your head into the wall, let's go through these. That is perchlorate. So, when you go to name it, you say, okay, acids containing oxygen. Okay, this, in its powdered form, is, gotta name it normally, hydrogen perchlorate. But once it's aqueous, right, you go with the root name, you say perchloric acid. Holy moly. Okay. I didn't leave myself enough space over here, so I'm going to put a little dig at myself. But if I was going to name these acids, which saves us a bit of time, this right here, right, is, this is not perchlorate, this is chlorate. So if it's an 8, it's going to be one of these. So we'll call this chloric acid. It's an ic acid, because it had an 8 name. Okay, making sense of this. This little fella down here is chlorite. That's hydrogen chloride. So we're looking at one of these ites. Oops, back here. One of these ites. So this is chlorus. The ites get the us, acid. Okay. Now there's a pain in the butt, because this one, you notice that was ClO4, and that was ClO3, and that was ClO2, and you see it going down, and okay. These get polyatomic individual names, okay? This one, this being hypochlorite, it's still an ite, so that's hypochlorite right there. Well, you're going to say that this is hypochlor, and we just leave off the ite, us acid. Bang, done. Okay, so we went through our binary acids and our 8 acids and our ite acids, and we kind of have that down pat. Bases, much kinder. All you got to say, what's that? What's the first thing? Sodium. And what do bases have in them? Hydroxide. Good, done. You're going to like this a lot more. What's that? Magnesium. And what's that? Hydroxide. Oh, this is a breeze. Yep. What's this? That's ammonium. And second part, hydroxide. Done. Easy peasy lemon squeezy. Okay, so when we think about acids and bases in solution, right? Acids have H plus ions, right? Those are known as cations. And bases have OH ions, which are hydroxide ions. So when you're checking this out, you're like, okay, so really, what's going on? As hydrogen increases, right, this is a game of opposites. If the amount of hydrogen is increasing, right, then you don't have as much hydroxide. So that decreases. And that's also vice versa, right? If you go in this direction, your OH is going to go up, but your hydrogen is going to decrease. So we've been talking about pH, but you could think of proportion of hydroxide. That's another system that's coming at you in chemistry. You heard it here first. All right, we've gotten to the end of this lesson. Hopefully I haven't driven you crazy, but you're in a review section. And what I like to do is I like to give you a chance, take some of these questions out for a spin, right? And see what you know. Now, in this case, it's going to ask you about these different indicators, and you'll probably have to look it up in your digital textbook or online, because I remember I said there's different indicators, and they're kind of cool. For example, indigo carmine, there's some of these ones will have color where when you're going from a blue, say for example, and you're going to a yellow, and when you kind of get part way in between, you get a bit of a green. Well, think about it, blue, yellow, kind of makes green, kind of tells you that you're going through a transition between sort of one pH and another pH. Check these out online and it'll help you, because they're asking about coffee with a pH of 5, and they're saying, okay, if you had these different indicators, what would they look like in a pH 5? Folks, some of them don't even change if it's not in their custom range. So here's where you get to go do a bit of homework, okay? Do your homework on these, check them out, right? There's the red litmus and there's the blue litmus. Remember, red goes blue in a base and blue goes red in an acid. And phenolphthalein, it's either colorless or it turns pink, right? We went over that one. So take these out for a spin, and I'm going to say pause. When you come back, I'll tell you the answer. So, pause. Okay, folks, assuming we're back, what were the answers? There you go. At a pH 5, indigo carmine's blue, methyl orange is yellow, and bromthiamyl blue is a lovely yellow. Second question, test tube 4, in this case, is showing acidic characteristics. Red litmus only changes in a base. It didn't change. Blue litmus went red. Must be an acid. And phenolphthalein, well, there's no color change at that point, right? It didn't turn pink. So we're looking at an acid. Okay, next set of questions. Pause. And we're back. So, which one's going to cause blue litmus to turn red? Probably has to be an acid. There you go, lemon juice. When they say liquid alkali, alkali is something where they're talking about something having a basic pH. So which of the following would be like a liquid base is what they're talking about. Liquid base that was poured into the Grand Canyon. There you go. Alkalis, a lot of the alkali earth metals, right, like magnesium, that's an alkali earth metal. And we talked about they form some of the great bases that we know about when they combine with water, okay? What's the name of HCN? Okay, that's cyanide, okay? Hydrocyanic acid, cool. Some more review questions, pause. And we're back. So the answer to the first one is that, 10 times concentration changes. And what compound is best represented above? Taking a look at the atoms, what do you think it is? Right? It's choice C, based on what you can kind of see. They're just showing you the different structures, right? So 1, 3, and 4. Lovely. Review questions, pause, take it for a spin. We'll come back. A mixture of lemon juice is basically being checked with 2 indicators, right? What is the color of the mixture? Green. So it's basically just a color mix of the 2 indicators, and what would they look like if you put them into an acid, right? There you go. Just kind of have a color mixture that's going to give you green. What is the name for the compound H2SO4? Well, that's sulfate, so that's one of those 8 ions. Sulfuric acid. The water from the Great Lakes in Utah has the following effect on acid-base indicators. What's its pH? So you've got these 3 conditions you snooped. So if indigo carmine turned blue and phenolphthalein turned pink and bromthiamyl turned blue, we're talking about something that is in the range of about pH 10. Okay, ladies and gentlemen, I'm going to take a break from this. I hope you get a chance to review this. This might be a lesson that you'll have to take a gander at multiple times, and you have to apply. So there's an assignment that's going to come at you for naming acids and bases, and we just need to get it into your skull. And you guys are smart. You'll have no problem. I'm convinced. All right. And remember, if you have any questions, always contact me, right? Don't play shy. I get bored easy. I love to talk to my students. All right, you guys have a great day, and we're out.